Okay, so we're gonna get into chapter 13 here. The force, and acceleration, and we're gonna study on a particle here. All right. So even though we have like a three chapter objectives, since this is a non-calculus based course, we're gonna hit only the very first one, yeah. And of course, I will talk about this a little bit, but you are not responsible for getting it, yeah, to solve these problems because they're heavily associated with the calculus, yeah, operations. So anyway, like your derivatives or your integrations, okay. All right, so let's get into the Newton's second law, yeah. I gave you a review for your Newton's three, yeah, first, second, and third law. But here in this chapter, we're emphasizing on the second law, yeah. So if you have a little particle, right, and that's subjected to an unbalanced force on it, and that particle is going to go in motion with acceleration, yeah, and the magnitude of that force, right, is going to be your mass time and that acceleration. Okay, that's all is set. Because the particle got to be subjected to some sort of a force in order for it to go in a motion, yeah. And we are dealing with a formulation. Okay, we call this a formula. So a formulation of that motion. Okay, so got a force on it, and it's gonna go with a velocity in a straight line. Okay, and we can calculate the amount of force by multiplying that two factor, which is the constant mass. Mass is always constant because that is a particle's mass. It doesn't really change in that amount of time, of course. And then your acceleration, which is your change in velocity of that particle, because it might have started with a zero velocity, and then get to velocity, so there's a change in velocity, and so the particle started to gain acceleration of some sort, and that's happening in that time interval. Again, operation is multiplication, so every time you have an operation multiplication, what you're doing is you're adding that many times, exactly the same as you can go with a at m times or m at a times, doesn't really matter, it will give you the same magnitude amount. Since this little m doesn't change, constant means it doesn't change in that moment, we can also write in the rate of change of momentum, because we can be able to write acceleration in terms of velocity, and when we do that, you have another multiplication operation between mass and velocity, and we call this quantity, okay, momentum. Okay, so you're gonna have a delta mv divided by delta t. Okay, so dmv by dt. So now we have this, right, force, the same thing, but in terms of velocity or momentum, and change in time. Okay, so again, don't forget your velocity. If you want to go another step down, is the change in the position, which is your displacement. You can also say change in distance over time. Okay, so make sure you know these only just by looking at A. You gotta know the change in velocity, you gotta know change in momentum, and also of course you can put this another delta S divided by t, which would give you the next equation, which is delta t squared. But I'm not going to go into there because your textbook cut it right here. Well, that's all about Newton's second law of motion. Physically, you can feel your force. Okay, if you wear this particle, we are subjected to unbalanced forces all the time. Coming at us from the external environment, right? You can feel the force, of course. You can also feel the momentum. If you have acceleration, that's the force. if your acceleration is completely zero, yeah, you don't have a change in velocity, meaning you will have some form of velocity, yeah. Because the change is zero, meaning like you might be, yes, having a constant, yeah, velocity at that time. If you wear the mass, yeah, if you wear the particle, you're subjected to the velocity, so you do have the momentum. And if you wear the particle, you could feel, yeah, that momentum. So anyway, make sure you understand the force and the momentum. Okay, it's the same thing. It's just differences is like when you don't have the acceleration, yeah, or when you have the acceleration with some sort, you also have the momentum, yeah, and you do have the force, which is bigger. You know that, yeah. Here you can see this force is, yeah, directly proportional to this, inversely proportional to that. Okay, so you can be able to understand the magnitude, right, of force is this entire thing, yeah, which you are dividing that with this, yeah. So therefore you can understand if the momentum is greater than the force or the force is greater than the momentum, depends on the situation or depends on the problem's condition. Okay, because even though we concentrate in magnitude, yeah, we also have to consider, yeah, because of their vectors, quantities, we also have to consider the directions, yeah, where they're going, yeah. Okay, anyway, that's for your Newton's second law of motion. Then we're going to get into gravitational law, yes. That's your Newton's another law. It's about the attraction between two particles, yeah. We call it the gravitational because we usually, yeah, put our second, right, a particle as our Earth. So I'm just gonna go ahead and write this down here, yeah, EARTH. So you know, we're talking about our planet right there, okay. So this, all right, Earth has a pull, and we call that gravity. Okay, gravity is always pulling the particle, any particle, of course, any object, anything, towards the center of it. Okay, so if you had like a mass 1, right, particle, right, and then it's, yes, situated right near to the Earth, then that would be the acceleration that particle, yeah, is subjected to, right? And they are that distance away from each other, yeah, from the Earth and the mass, and you will have an attraction force, okay, meaning like the Earth is kind of pulling, all right, this mass towards it. Otherwise, we would be, yeah, we wouldn't be on the surface of the Earth, yeah. Because of the gravity or gravitational force or force of attraction, yeah, we stuck on the surface of the Earth, and then we can move around, of course. And we also have the atmosphere, yeah, our cover shield. Otherwise, you'll be disappeared right into the straight into the universe. So anyway, so that kind of force exists, yeah, anywhere in the universe between two particles. Of course, your particles is not a little tiny particle. It's really giant, you know, gigantic planet objects in the space. Of course, they have their own different gravitational pull. Yeah, so the constant G is going to be different if you change the system from Earth to somewhere else. Okay, it's not only Earth, right? You can also apply this on lower, in between any, all right, two particles, all right. So between any two particles, so it can be anything, two little tiny particles or two giant particles in the universe, or two little tiny particles inside of your body, yeah, or two objects on the Earth, yeah. whichever way that you want to do, okay, there is a force of attraction between two particles, between any two particles, okay? And that pull force is called the force of gravitation between that two bodies, okay? And that is Newton's law of gravitation, okay? So here, of course, we brag about it. That's your force of attraction between the two particles. G is a universal constant of gravitation. And then your mass, right? Mass 1, mass 2, so mass of each of your particle. And then R is your distance, yeah, between the centers of the two particles, all right? I should put this little thing actually to there, yeah? Drawing is really sloppy. Make it a little bit better, yeah? So anyway, so that justifies the center, yeah? It's got to initiate, the distance got to be measured from the center to the center. So don't forget, if I ask you, and some of the tricky question would have like a distance from here to here, but you gotta understand the distance is starting from the center, okay, all the way to the center of the next particle, yeah? So don't forget your radius, to add the radius of that and radius of this to this distance, okay? So that's a pretty tricky thing. Why? Because look at this, okay? When you read the description of a formula or equation, you got to read it very, very carefully, okay? And understand what you're reading. So that's the distance between the centers of the two particles, okay? Some of the problem in some of the textbooks, they ignore it, okay? They've been ignoring the radius, so that's actually wrong. However, I have come across a couple of textbooks, doing that. I don't know, that's the author's mistake or whatever. So just pay attention, you have to include the radius. Okay, anyway, so let's go to the next one. This one is included in your non-calculus based dynamics, and you definitely need to know your weight and your mass, So now we are studying almost everything on Earth. So this G is again your acceleration due to gravity from your Earth perspective. So that's about 10 meter per second square. Sometimes I'll give you 9.81, sometimes I'll give you 9.8, sometimes I'm going to give you just 10. You should be able to know how to convert between two unit system, so your SI or metric to your foot-pound, which is your British, Anyway, so your weight is equal to, again, mass, right, times gravity, Here you're dealing with the two constants. Here mass is a constant, and then your gravity is a constant for planet on Earth, okay? So pay attention, again, your multiplication, you are adding that many times, you're adding this many times, all right? Pay attention to details. Unit here, mass time gravity, which is your acceleration, is going to give you Newton, and that is, meter per second square, G is, which this little guy. Of course, your mass is going to be in, for SI unit, mass is going to be in gram, right, or kilogram, So that's going to give you mass time acceleration unit will give you Newton. Yes, so you have to know what Newton, okay, a unit is. And of course, I don't want you to forget your force, right, unit, which is Newton. Your weight, again, unit is Newton, because it's the same thing. Your forces, I'm going to go back here one slide, F is equal to ma, okay. So that's the same as your weight, In weight, your acceleration is a particular acceleration if we think about our Earth, that's a g, 10 meter per second square. Here, your acceleration is the acceleration that the particle is traveling with, So, but it's the same thing. Your mass time acceleration, So therefore, the unit is Newton for force, Newton for weight. Okay. Don't forget that. So Newton is nothing but it's just kilogram, meter per second squared. That's your acceleration, and this is your mass. All right. So here, if you have like a 1 kilogram block, right, and moving with acceleration 1 meter per second square, you will have like a 1 Newton force. Okay. So make sure you pay attention. Your F is equal to MA, and also I put the unit here for you. Okay, so I wrote this for you, So when you read this, you can be able to understand how we ended up getting this weight, equation. Okay, so here I wrote it for you, okay? It's a little bit long, so when you read it, you're kind of like, oh yeah, how did that happen, So we know that our gravitation, a force in between two, particle, we have F, and we can write it this way, and thus, you also know that your force is MA, right? So now, if we're dealing with the gravity, gravity means acceleration due to gravity, to our Earth, then we can write A as a G, So now I am going to move this to the other side, okay? So when you move your mass to the other side, you get G is equal to F divided by M, And your F is, of course, this whole thing, yes? In this case, we're looking at, it says, let's give M1 as the particle 1, is M, so I just put an M here. And then, of course, your second particle is your Earth, mass, mass of the Earth. So I put the mass of the Earth right there, okay? So we get this. So your gravitational, acceleration, so we also call that G, little g, acceleration due to gravity, is this divided by that, okay? And so I'm going to put this whole thing down here, and the m is 1 by n here. So you can do two things, okay? One is you can cancel this out and can be able to write your acceleration due to gravity in this way, okay? Your gravitational constant, and then your mass of your Earth divided by r squared. You can calculate the acceleration due to gravity, okay? You can also bring it down, right? Just straight down like this. So let's just move it.
I didn't catch that.
I'm gonna turn in this. That's my robot. Okay, anyway, so pull it down, And so you can also go this way by putting this little m to that side, okay? So you have your gm, and then you have this, which is your force, of course. Like that, now I'm going to move this to this side and move that to this side, okay? It's the same thing. So this is anyway is a force, and we are going to write it W, right? Another symbol. It's just a force, of course, force of attraction, and we're going to write it M, and then G to the back. So this is how we get W equal to mg, in a non-calculus based derivation, So if you're reading your textbook and you don't understand, the change in your formulas is or equations are like that, it's just a purely algebra to change a position in the equation, okay? All right. So anyway, let's go on to the next one. Here it's just showing you the SI system in your foot-pound, right? The second system, your British system. Another way of calling it anyway. So here is your masses in kilogram, your weight is in Newton, your acceleration is in meter per second square, At that time, your force is, of course, your Newton, so that's m times acceleration due to gravity, right? Then that's your g, 9.81 meter per second square. And also don't forget, your universal constant or gravitation. Yeah, it's just a constant. And don't forget there's a gravity, little g is also going down. It's just right in here. Yeah, even if we loosely say it like your acceleration due to gravity is in there, it's because let's go back to here. See that? There's your g. Yeah, and this is your acceleration due to gravity, and this is a constant, and that many factor, is where we get this number, right? 66,173 is because your g is 10. Yeah, and here your mass of the earth divided by r squared is the distance between the earth and your particle, times, and then your constant. So if you want just the constant, you're gonna get this to that side. Okay, I can write that down for you. It's a little bit complicated, but you can get it. So here I do this, okay, derivation for you. So we can of course change it, to this site. So that's pretty easy. All you have to do is just get rid of this and put it like that. Okay, so see, so that's how we get this. Let's go back here, this constant. Okay, so we loosely say like, okay, there is a acceleration due to gravity is in here, but it's of course that's your gravitational constant. And when you multiply your g, which is this little guy right there, I'm gonna put a space here so you can see, along with all of this, your distance, your divided by your mass, right, your particle mass, and then multiplied by your another second particle mass, and you're going to get this. Okay, of course in this case the second particle is your earth, so the mass of the earth, so you get this g, and that's where this constant, okay, came from, right? So just be very careful. Even if we write like, oh, there's a constant like that, I would add another one here for you, because if I say it, you wouldn't get it. It has nothing to do with English. It just physics. Okay, so your g would have like this at the same time as that. You're gonna have a confusion between that two, because people loosely say like, gravitational constant, gravitational constant. This is acceleration due to gravity, which is also a constant. Okay, this g based on that g, and you calculate this way. Okay, all right. Complicated, even if it is a non-calculus space. Okay, anyway, so let's go to the next one. So go back to our SI unit system, go with your Newton, and at that time kilogram, meter per second square, and your Newton. Your foot pound second is your British system. We're gonna go with slug for mass, and then your feet per second square, is in there, your acceleration unit. And then your weight, of course, is in pound. This is a system you use every day. Yes, that's two unit systems. So make sure you can be able to change, convert the units in between them. So review your mathematics for conversion. I'm not quite sure. Do you want me to go over the conversion, unit back and forth, or you're okay with that? Please, think about it and let me know. So for this class, we only cover 13.1. So the rest of them is up to you. You can read it for knowledge if you want to. And if you don't want it, you don't have it, but it's definitely not going to be in your exam. Okay, this is just telling us life isn't that simple like this. Okay, no, not just this. Okay, so that's too perfect. Life is like this. You have, just like I said it, you have many different kinds of force. So there's not only one unbalanced force subjected to a particle. There are so many forces, many different kinds. So that's the sum of your forces, going into that direction anyway. Because in real life, more than one force, is acting on a particle, on a body or an object. You're being subjected to many different forces without you actually noticing it. That's why you need energy to balance these action forces on you. You have the same amount of force that you have to exert from your body back to them. Otherwise, you won't be in balance. So that's a lot of energy every day that we need to do what we're doing, and that's the reason why you age over time. So anyway, so what we do here on calculus base, or getting into calculus base from this, 13.2. So your vectors, of course, summation, but your force is a vector. So we add all of the forces all together in this way. And then calculate, of course. So here you can see this is what we call a free body diagram. We use it all the time for all calculus based. And then this one is just showing you your F, your force going with an acceleration, your little particle mass. So this is your kinetic diagram, what we always draw. And then this one is your free body diagram, okay, showing you more than one force right in there. Force 1, force 2, blah blah blah. Of course, this life isn't that simple. So anyway, so from here is for you to read, okay. And inertial reference frame is just telling you, right, you're like saying in a car, you're definitely subjected to a forward acceleration. You can feel, like I say, you can feel the force, you can feel acceleration, even velocity, and your momentum, of course. So people always think like, oh, it's caused by a force, right? You can feel it. And we usually say everything that we feel about is just force. Sometimes it's velocity, sometimes it's acceleration, sometimes it's momentum, right? Depends on the intensity of that. But we call it all force anyway. So the sensation that you get that you thought it was a force is actually, it wasn't a force, right? That's just your inertia, inertia. Inertia is nothing but your resistance, to the change in the velocity. Okay, here you're moving, so you can feel that change. All right, you resist. You're resisting actually to the velocity change. Okay, because you don't want to. Your body always trying to balance itself. And it tries to resist the external force like that. Okay, so anyway, so that's what you're feeling, the resistance. So if we have to put in the diagram, vector diagram, of course, so this is a path of a particle going, and then this is your velocity, so going in this direction, your acceleration going in that direction. You have two things going on, somebody walking, and then here is the particle path, the inertial frame of reference is happening on this axis. Okay, right now you wouldn't understand but for now, just take it like if you have, right, going forward with an acceleration, you will feel the change in the velocity because your acceleration is the change in velocity. So let me copy my equation back. So here is your equation, your change in velocity over time, so that's your acceleration. So that change you are resisting, okay, and we call that inertia. And that is actually true for any particle with a mass. So resistance of your mass to a change in velocity on that mass. Yeah. All right. Again, we're not getting into this, so if you want to read, you can go ahead and read. 13.3 is covering just the equation of the motion for a system of particles. Again, see, system of particles. Even if we study one single particle, of course, in reality, there are so many particles, right, in a system. And we call that the inertial, right, inertial coordinate system. Yeah. So look at all the factors diagram right there. Yeah. You have force. I mean I number of force. Okay. Now here's your axis there. And particles, of course, going crazy. And they have their own mass times acceleration with their own movement. Yeah. So this is just a little tiny thing, but at times billion of them out there, yeah, in the atmosphere, inside of you, outside of you. Oh my gosh, you name it, yeah. So this is a particle world. We are built of particles, from the little tiny one all the way layer by layer, yeah, physics. All the way down, you have your quantum, and then your physics level, and then your chemistry, yeah. Your chemical level, and the aggregation of the chemicals become your protein and all kinds of stuff, bio level. So if you think about the levels of life, there's a lot of stuff, yeah. So you're actually living things are built upon particles, yeah, inside, up, of course. So life is just a lot of yes. There are many subsets of life actually. Life is a real compilation of all the subsets of life after life, layers happening inside of you and outside. So anyway, you gotta understand so many particles in the system. We study by the system, yeah. Of course, we will apply the same thing for the motion, and there are so many of them, yeah, and that many, which is I, just keep going, yeah, that many numbers, yeah, you can be able to calculate, of course, getting complex and complex, even though the little equation is saying like, oh, the sum of the or forces is equal to, yeah, and you have your mass, the particle mass, a time your acceleration, yeah. Oh my gosh. And this is just showing you what system you are in. Yeah, you have your solid system, liquid system, and gas system. And of course, you can get the estimation of these forces. So everything that we know are not absolute. It can never be absolute. Yeah. Anyway, so let's go to the next one. Important points. You can just read about it, reiterating the same thing. Yeah. Going into the equation of motion. Again, experimental evidence. Think about your limitations. Yeah. And your inertial frame of reference. Yeah. So playing in between your mass, your velocity, your acceleration, your momentum, and then your inertia, yes, resistant to a change in velocity, and then of course that your time, yeah, change a little bit of time or a great deal of time, think about it, but it's always in a interval, right? Time interval happening, and time again doesn't exist. The time that we were thinking about just the measurement, yeah, we're measuring from one reference point to another with some device, yeah, equipment. So anyway, everything that is happening is all your events. Okay, so the equation of motion, of course, yeah, you have all the equation. We have seen several equations already, yeah. Your FMA, this is, yeah, repeated here again, your unbalanced force on a particle, yeah. Cause it go with an acceleration, so you get your force is equal to mass time acceleration, and then we link acceleration to velocity change, yeah, over time, and then velocity into the displacement over time. Okay, so make sure you get all your units as well, and then it gets into inertial frame of reference, yeah. Usually they don't this frame, okay, doesn't rotate. So the little diagram we just show you, so that's going with your coordinate axis, and then they're going to translate with the constant velocity. Sometimes they're at rest, right? Your mass is a property of matter, of course. Everything that we know here in this world, matter, yeah. Things that we don't know, we call it anti-matter. We believe that it does exist, beyond our, of course, intelligence at the moment, but we believe that we could be able to get to that point to study. Yeah, so these are ongoing progression and studies. So anyway, so that provides a quantitative measure of its resistance to a change again in velocity. Okay, so every mass is subjected to many different kinds of imbalanced forces. Every imbalanced force can cause acceleration to move that particle, but the particle doesn't want to move. Yeah, it wants to resist, and we call that inertia. Yeah. We also have absolute quantity, and because your mass is, and also it is a constant, don't forget it. Yeah, and that's what it's saying. It doesn't change, yeah, from one location to another. So your mass is constant. Your weight is a force, of course. When your acceleration is acceleration due to gravity, which is based on your Earth, yeah. And we study about how to get the constant, a big giant G. Okay, your little tiny G is your acceleration due to gravity. Your constant G, we can be able to calculate it out of that acceleration due to gravity. I already showed you the equation. Okay, it's not absolute. It definitely depends on the altitude of your mass, yeah, which is your distance, of course, from your Earth's surface. Well, the center is better, actually, not surface. See, this is what I'm talking about. Some textbook author have a confusion between the center and the surface. Yeah, so you will come across that in many different textbooks. Okay, but the real thing is you have to measure from the center. Yeah, of the Earth. Alright, the next one is a 13.4, so we'll get into the rectangular. Alright, coordinates. I'm not going to go into any of it, yeah, because you need calculus to calculate them. Of course, we can do one or two forces add up together, but we're not responsible for that, yeah. All you have to just know the concept, yeah. That's about it. Here is our coordinate system in 3D. Of course, we have a different, look at this, 1, 2, 3, force diagrams right here for this little, tiny particle in there. And we're going to study, of course, according to the axis, X, Y, and Z. Yeah, here is your, look at that. This is your rectangular coordinates that we're studying. Yeah, so you have three different, sum of forces, which is along the X, along the Y, and then along the Z, right? They have, of course, their own acceleration. Okay. Alright, this is just a procedure for analysis. Again, you don't have to go into it. Yeah, we will do the calculation. Yes, non-calculus based calculation, easy one for you. But you can read it if you want to. Don't spend so much time on that. 13.5 is equations of motion, normal and tangential coordinates. We're now studying a different coordinate system. Rectangular, now we're dealing with the tangential. The same thing, we're gonna study, right, Tn and then your B, okay? So again, your B axis here, T, and then here is your O, right? This is just a tangential coordinate, not the coordinate systems, yeah? But the same thing, you add them up, yeah? With their own acceleration. And that many forces, you sum them up, yeah? Alright, let's go to the next one. This is just showing you your roller coaster falls downward. Yeah, down, see that along the track. So the cars right there, have both a normal and also tangential. Because see, this is a curve anyway. So you have normal, that's 90 degree, straight. And then this is tangential, it's of course a tangent to this curve. And so these are the component of your acceleration. Now we're studying the acceleration G, and you have a normal component and you also have a tangential component. Alright, again, procedure for your analysis, blah blah blah. You don't have to go so much into it, And here is somebody, we can take this as a particle, and there is an unbalanced force, which is this little guy, rho. And this guy is your skier, of course. Okay, it's going to give that person a normal component of your acceleration, because it is go straight on 90 degree down on this, were in the tangential coordinates, yeah, so A and B, and then your T right there, which is this guy, yeah. Okay, so let's go back. This is in your textbook, so you can play with it. There is an interactive, yeah. Again, just telling you about your normal and tangential coordinates, yeah. So pay attention to the direction of your car's tendency, yep, to slide your normal force and also the frictional force. All right, change it and see how they change. But again, you're not responsible for any of this. Just read it if you have time. Yeah, 13.6 is your cylindrical coordinates, so different kinds of coordinate system again. Here we break it down the same thing with different velocity, yeah, a different coordinate. We're gonna add them up, yeah, your forces in the axis. So this time you go with R, theta, and C coordinates, yeah. All right, and here's another picture of your roller coaster, yeah. You're dealing with a spiral path right here, and that's an example of your cylindrical coordinates, yeah. Okay, and tangential and normal forces. Here again, your curve, tangent, this, all right, is how you draw your force diagram. Your forces go in this direction, okay, and then you have your P and N subjected to it, yes. And of course your angle, you know, the distance is all that much. Another tangential and another tangential force, okay. Again, tangent is on your curve, and then your normal is perpendicular 90 degree, yeah, to the particle. Okay, so we don't have to go in details with this. These are all calculus based, by the way. This is just showing you, yeah, how the particle is moving, and this is another tangent equation which come from here, yeah. Just for reading, your analysis, yeah. If you have time, read it, but don't need to go into that because it's not in your tests, yeah. We don't have it in your assignments either. So 13.7 is your central force motion and your space mechanics, okay, the same thing. If you have time, you can read it. If you don't have time, don't read it, okay. It's just telling you, like, if your particle is moving, right, under the influence of a force, you know, there's a force right here, and you have a line of action, and that line of action is always, yeah, pointing toward a fixed point, okay, pointing towards a fixed point. At that time, we're gonna call that's a central force motion, yeah, okay. And that type of motion is, we use it for electrostatic and also your gravitational force, okay? Because it's pointing towards the center of the earth, yeah? So anyway, no need to get into any of the details. And so we're just skipping on all of this. Newton's law of gravitation, we already talked about it, yeah? Your force is gonna act between the mass centers of your earth and also your other particle. In this case, your satellite is the M2, of course. ME is your Earth, yeah, mass. M is your orbital satellite is mass right there. And the distance between the Earth, center of the satellite, yeah, is your R. Square it times your G constant, yeah, universal gravitational constant, which is based on your acceleration due to gravity, is going to give you your gravitational force, okay. Now this one you have to know, yeah, that's in your section 13.1. So chapter 13, very easy. You only have to hit 13.1, okay. The rest of them are just for you to read, okay. Here it's the same thing. You launch, blah blah, yeah. And there's your negative F going towards this little particle in orbit, yeah. They have a distance, of course. Be careful with the center, yeah. This one he get it right, yeah. And then this is your curve, yeah, your tangential curve right there. The free flight tragedy, we call it, yeah. And that's your power flight tragedy. But don't worry about the tragedy, it's just a curve, yeah, if you know about this, alright, and then you launch it. So these are the forces that we study, the distance, yeah. Again, we're looking at, just we call that 2, particle 1 is mass, and this is mass 2, yeah, mass 1 is right here on Earth. So anyway, so let's go into there. Since you're dealing with a tangential, yeah, path, of course, yeah, you have to deal with your wave, which kind of like waveform, which contains the angle, yeah, and that's why you're seeing these cosine and sine stuff, yeah, right in there. Okay, so let's get into another one. Same thing here. It's a continuation, yeah, of your equation and derivation. You don't have to know any of it, yeah. If you have time, just read it. Alright, so let's go into blah blah blah. Yeah, these are just a tragedy. Yeah, you have hyperbolic, parabolic, yeah, elliptical, and then your circular tragedy, and keep going. Yeah, I wanted to put this in you, but then I was thinking whether I should or I shouldn't, because this is just showing you your velocity. Yeah, you can be able to calculate that, which is linked to our very first equation, of course. Yeah, so you might want to, yes, I would say yes, study this parabolic. Yeah, and I might think about elliptical orbit to put into it or not.